Good morning. Today is June 8th, 2019, and this is the John Chappell Natural Philosophy Society. And today, Ian would like to bring us a recording about the solar eclipse experiment, which brought Einstein to the forefront and verified general relativity, or did it? So why don't we go ahead, Ian, and why don't you play that recording?
So just to say, Franklin, that this recording was played on a commercial radio station, an FM station here, just a day before the centenary of the experiment, which took place on the 29th of May, 1919. And there was a professor, Peter Coles, who's a professor in the University of Maynooth. I think he's a joint professor. He's also professor in Britain as well. But so I thought we might just listen to it. It's about 13 to 14 minutes, and then we can analyze it. So I'll start it now, Franklin.
One that made the name of potentially the most famous scientist of all time. It was on May 29th, 1919, during a solar eclipse, that the first ever measurements were made, testing Albert Einstein's theory of general relativity, and they proved that the Austrian physicist was right. It made Einstein the global star and had a major impact on the 100 years since that experiment. But you're wondering, what is Einstein's theory of relativity, and why was it so important that it made him a global star? John Coles is Professor of Theoretical Physics at Maynooth University, and he's here to explain. John, good morning.
It's Peter Coles, actually.
John Coles was a political correspondent. Yes. He was. So, sorry, Peter. That's what I was thinking of. Tell me, first of all, if you can, in layman's terms, what is the theory of relativity?
Well, we're talking here about the general theory of relativity, which Einstein came up with in 1915.
Because there is the theory of special relativity.
Yes, that came 10 years earlier, and it contains the core of the ideas in the general theory, but not the full theory. The general theory is really a theory of space and time, and gravity is a manifestation of space and time in Einstein's theory. The curvature and warping of space produces gravitational fields.
He did thought experiments, Einstein, and one of them was you're on a train that's departing at the speed of light, and you're looking at a clock tower, I think in a town he knew well in Austria, and if you're departing at the speed of light, the time on the clock would remain exactly stationary, whereas if you're in the town square, it's just carrying on as normal.
Yeah, so there's basically the whole idea of Einstein's theory, both special and general, actually, is that both space and time are relative. They depend on the situation of the person who's measuring time and looking at space.
Yeah. Now, we all know, if you're going on a motorway and you're doing 120 kilometers and someone passes you doing 140, then if they should bump into your bumper, the collision is only a 20 kilometer an hour collision. If he's coming the other way, it's a 260 kilometer collision. So we all understand innately relativity in terms of speed.
Yes, but that's only for really small velocities you're talking about. Although you might be speeding on the motorway, you're still going a lot less than the speed of light, which is the crucial yardstick, if you like, by which you have to judge whether things require relativity to explain them. And so the eclipse experiments of 1919,
is the one that happened 100 years ago tomorrow.
Yeah, 100 years ago tomorrow, involved light traveling from distant stars along a line of sight close to the sun. And light, actually, the crucial point of general relativity is that light travels through a space which is warped by the gravitational effect of the sun. And consequently, the light doesn't travel in a straight line. We're used to thinking of light going in a straight line.
We use lasers on that basis.
And they do go on that basis because there's not strong gravitational fields nearby, fortunately. You don't use lasers near a black hole, for example. Now, the point about this is the light gets slightly distorted on its journey, and the idea is very simple of this experiment, is that you take a picture of a part of the sky, measure the star positions very accurately, as accurate as you can, at night, when the sun's nowhere near. Then you do the same measurement during an eclipse with sight to the same stars.
Yeah.
And if Einstein's right, the positions of the stars should look slightly different on the photograph with the eclipse
Because the light has been bent.
because the light has been bent. Now it's a simple idea. Two photographs, you just compare them and you look at the positions and see what they do.
Today, we could do that, no bother. The kind of equipment.
Yeah, and in fact, it turns out using starlight is not a very good way of doing it. We can use radio and all kinds of other methods for doing it. It's been established. The problem is that it's really difficult because the main difficulty about doing these experiments during an eclipse is that you don't have an observatory underneath the total eclipse. You have to go out in the field and use portable equipment. The effect is tiny. It's what an astronomer would say is 1 second of arc. If you want to know what that is, it's about the width of a human hair, at a distance of 10 meters. That's the angle.
That's the angle, so it's tiny. It's the most acute of acute angles.
Yes. It's really difficult to measure.
Who did the experiment, first of all, and what kind of gear did they have?
Well, actually, it's a good point. All of the gear that was taken was actually manufactured in Dublin.
No.
Not a lot of people know that, but it's true. It's made by Howard Grubb's telescope works in Dublin. So they took what are called astrographic telescope lenses. So these are 12-inch or so object glasses, lenses, old-fashioned refracting lenses, and they put them in steel tubes. And because you can't, if you haven't got an observatory, the telescope can't track the movement of the stars through the sky as the Earth rotates. So the telescopes are actually mounted horizontally, and there's a mirror near the aperture of the telescope called a coelostat, and the mirror rotates slightly, and that corrects for the Earth's rotation. So basically, the light from the stars goes into the mirror and then is reflected into the telescopes. The experiments, there were two measurements. The path of totality of this eclipse ran across the Atlantic from northern Brazil to the West African coast. The two guys, the person who led the Brazilian leg of the expedition was Andrew Crommelin, another Irishman.
Yeah.
The more famous individual who went to Principe in the Gulf of Guinea was Arthur Eddington, and he is the name most strongly associated with this experiment because he kind of led all of the analysis, and he fronted the announcement of the results in November 1919, about 6 months later.
They must have had tremendous confidence. I mean, their measurements had to be so exact, and the tolerances are so impossibly narrow.
Yes.
It takes great nerve to come out and say, yes, we have verified Einstein's theory.
And it wasn't without controversy at the time. There were people who didn't believe it. In fact, Eddington was practically accused of having fiddled the data. It didn't really go to plan in the expeditions. Eddington's own, he had bad weather, and he only got a few measurements. And the plan that he adopted to try to analyze the data, he couldn't do that, so he sort of improvised a bit, and people were suspicious about that. It turned out that one of the smaller telescopes in Brazil gave perfect results, and that was really clearly Einstein's. And if you're skeptical about this result 100 years on, actually all of the measurements are published in the paper that came out subsequently, and you can reanalyze the data for yourself. I've done that, and it actually stands up. The main point, of course, is that subsequently this kind of thing was repeated many, many, many times, and it's verified with better technology.
Could you please ask your guest if the light bent around the star returns to exactly the same trajectory, or is the path altered? In other words, is it kind of a little loop around where it was and then returning to its
just a slight deflection. I mean, the point is, imagine you have light coming towards you in a straight line. The light enters your eye, and all you know about is the direction that the light is entering your eye or your telescope, right? Now, if that path has been curved, you still only see the direction that it enters your eye, and your eye extrapolates back along that last part of the journey. So if there's a slight kink in it, you see the light from, you see the star that, or whatever sort of,
in a slightly different place.
Slightly different position.
Okay, so it does alter the trajectory. What was the impact of this then on Einstein himself?
Well, it was extraordinary. I mean, it's unprecedented. The press reaction at the announcement of the results. I mean, it did take 6 months to analyze the data. Einstein, it made front page news all around the world. The New York Times, the London Times, everywhere. There were these stories about revolution in the skies, and lights all askew in the heavens. The headlines were extraordinary. Einstein overnight became famous. I mean, this is the event that made Einstein a household.
And I'm sure his appearance helped, because he does look like the nutty professor.
And actually, there's an interesting thing that he was so famous that he was invited to appear in Variety on the London Palladium. What he was supposed to do, I have no idea, but he probably wisely declined that invitation. But he actually thought it was absurd, this whole fame. He couldn't go out of the house because he was so famous subsequently, and he regretted that, I think.
Now, the fact that his theory was verified, scientifically, what did that mean in terms of what happened in the next 100 years?
Well, it opened up a new branch of physics, really, a new branch of astrophysics, certainly. As I say, Einstein's theory was really a theory about space and time. Space and time previously had been thought to be sort of absolute things. Time always goes at the same rate. Space is just, it's the backdrop. Things happen in space, but it's not part of the action.
Yeah.
In Einstein's theory, that changes and space becomes a dynamical thing. And so that led to a whole load of new developments. Without this breakthrough, we wouldn't have got black holes, gravitational lensing, gravitational waves. More recently, we are discovering. And also, these very small effects, like this tiny 1 second of arc deflection, are now mainstream practical use. For example, your GPS system in a car would not be able to position the GPS system so accurately were the allowance for general relativity not included in that. So there's corrections for general relativity due to the Earth's gravitational field needed on the scale of the Earth as well, just to get the positions accurate.
Yeah. People wonder, does this have any impact? And you've just given one example of how it does in our daily lives. But to try and get a common sense handle on time going slower or faster, I mean, that's hard.
It is. And so that you get back, if you ask that question, you get back to the question, what is time? And there's only a circular reasoning argument for that, which is that time is whatever it is that clocks measure. And then you have to ask, what is a clock? And what does it do physically if it's in a gravitational field and you move the clock?
And we measure time, I suppose, by disintegration. We get older and we die. And that's how we record time. What about gravity? I mean, I know the laws of gravity, and Newton was the person who defined them. The idea that the reason a thing falls is because it's small and the Earth is large and it attracts the object to it, therefore it falls. But what is gravity? I mean, I understand light and photons and all of that, but what is gravity?
Well, gravity is in a way, the most mysterious of all the forces of nature that we know about. Gravity, there are other forces, there's electromagnetic forces and so on, which we kind of understand in a pretty complete way, including at very high energies. Gravity has defied that complete description, and even general relativity is not a complete description. It doesn't work in very strong fields and when there's strong sources of energy in it. Einstein knew that his theory would probably eventually be supplanted. What is gravity? Well, in general relativity, it comes up as a manifestation of space. So space itself is distorted, and that causes motion of particles of various kinds to be distorted as well, including light, of course.
Yeah. No, I've never really understood gravity. I knew what it did, but I was kind of looking for, interaction of subatomic particles with each other and, a great mass of subatomic particles on one side influencing a tiny mass of subatomic particles on the other side in the smaller object, and that's how they are attracted to each other, like magnetism.
But it's not like magnetism. It defies the same kind of description as magnetism. And gravity fundamentally is still not understood as well as we would like to understand it. But in general relativity, we do have a description of gravity. It's unlike Newton's theory. It doesn't involve so much of force, body A and body B and all that. It involves a whole look at the way time and space evolve.
Well, Peter Coles is Professor of Theoretical Physics at Maynooth University. There's still a problem for you to solve then.
Yeah, I'm not out of work yet.
All right, Peter, thank you very much for joining us. Now, coming up, one that made the name...
Okay, that's it, gentlemen. So, Franklin, I hope it wasn't too dry, but I mean, I think it could form the basis of a discussion. My own notes on it were basically that, well, apart from the obvious fact that the interviewer, by the way, he has a degree in chemical engineering, that continuity announcer, but he made the mistake that Einstein was an Austrian physicist a number of times. He started off by just really talking about the delay in obtaining a signal from light. If you're looking at a clock, say, and the time delay, which is probably pretty trivial. He then just talked about relative speed of two motor cars or something on a motorway or something like that, which is a bit trivial. I mean, that's nothing to do with special relativity per se. And in fact, special relativity disagrees with his simple additive or subtractive formula for the speeds of the cars. He then went on to talk about space and time being curved, that essential aspect of relativity. Now, he then said that they went out to see whether the light was deflected, and if it was deflected, Einstein was right. Now, that's a bit of a simplification, because and we can look at this maybe in a moment if you wish. Using Newton's laws, if you take light to be sort of like have some mass, some ponderable mass, and you work out the orbit, you get a hyperbolic orbit, and you get a deflection. Now, Henry Cavendish mentioned this in the 18th century, but the German physicist mathematician Johann Soldner, Soldner, did the calculation in 1801, and he got something like 0.88 minutes of arc. Now, so they went out to say, okay, that's the Newtonian value. Einstein did a calculation in 1911, which gave the same value, and in fact, he was accused of plagiarism. Because he didn't mention Soldner, but he redid the calculation in 1915. He said, no, that was wrong. It should be twice the value. It should be 1.86 arc seconds. So. Then Peter Coles talks about Eddington just for a moment, that he was accused of fiddling, but that the figures are all available publicly, and you can look at them, inspect them, and he did that, and he found that they stand up. He also mentioned the two expeditions, one to Sobral in Brazil and the other to Principe in Africa. And he said that the Brazil ones gave the good results. I mean, everybody knows that Eddington was pretty well washed out. But actually, I understand that most of the Brazil results were discarded because they were not of the right order. And they said they must have been affected by temperature effects. And they selected just a couple, 2 or 3 results that seemed to be all right from the Einsteinian point of view. He also said subsequent experiments have verified. And again, I'm not so sure about that. I mean, it's very difficult to get the accuracy required. And then, of course, you also have the question of possible refraction due to the sun's corona of glancing rays. They say by 1967, or another thing on the web said by 1973, they did some radio frequency experiments which verified it. But I have my doubts about that. We might spend the moment for that. Just 1 or 2 other things. He then, towards the end, Franklin talked about black holes, gravitational lensing, gravitational waves have all followed from this. Compounding the error. He then went into this canard about GPS. Wouldn't work without this, and possibly one can talk about this gravitational effect on atomic clocks, but that mightn't be quite the same as saying that GPS wouldn't work without relativity. Then they finished off by talking about gravity being a mysterious force, and the interviewee admitted that GRT was not a complete description, and in the process of time it probably would be superseded. So I think those are all my observations, and I'd be interested to see what all of you think about it. Thank you.
Okay, well, I'll give you my take on that after listening to that. So that seemed like a pretty mainstream discussion about general relativity and special relativity, although I always have difficulty in figuring out what the difference is between those two. I mean, really, is there a difference between, I always get them mixed up. It's like centrifugal and centripetal force. You get those mixed up. It's like general and special relativity. And what's so special about the relativity? What's so general about the relativity? But in any case, so if someone wants to straighten that out, that might help. But in any case, there wasn't, I don't know, a lot of, say, really deep scientific content here. And in my experience in reading what happened during this experiment, the things that send up red flags in my mind is, this difference of a hair width at 10 meters, which is really, really tiny. And they're only using very small telescopes, things like a 4.5-inch telescope. I mean, that's a telescope like I have, which is easily any amateur can get a telescope, and it's probably of a higher quality than probably whatever Eddington was using back then. And if anyone's ever looked in a telescope and look at stars, you can see that they are just fuzzy little blobs that are kind of moving around. So me personally, I find it very difficult that that kind of tiny angle is within the error of the measurement error that you get with using optical telescopes of that size, especially portable ones. So that raises a lot of red flags to me, saying that they could not have possibly measured such a small change accurately, right? It's just outside the measurement error that's possible with such small telescopes. Now, the other thing I heard about this experiment was that while they did find some stars which did deflect in the correct amount and direction to confirm Einstein's theory, there were also other measurements which were in fact the other way. That in fact, it would seem like there was kind of like a scatter chart of stars. I mean, the stars would move this way, they would move that way, they'd move this way. So they found the couple that actually matched up with what Einstein predicted. And in science, that's called cherry picking, right? You can make any theory true given enough random data. So that would be the other red flag. Number one is that they couldn't possibly measure this thing carefully. Number two, the data contained contradictory data, which they ignored, right? And concerning whether this actually happens, we have one of our CNPS members, Ed Dowdy, who works for NASA, and he just strongly claims that all of the deflection happens only at the very limb of the sun and is due to the solar corona. Now, I personally think that that's a valid argument, and that anyone who wants to discuss this needs to be able to say something about why that isn't the effect. And they also mentioned these other, they've sent radio signals, and they've tried to confirm this whole effect. And Ed Dowdy claims that he has a chart showing that the amount of deflection is like 0.00000, right, until you get up to the corona, and then you see a deflection which would be consistent with his hypothesis. Although when pressed and I looked at what his sources were, I couldn't confirm that there is any actual data which shows that. Right? I mean, I'd like to agree with him, but he doesn't. at least to my satisfaction, he didn't show the data showing that there is no deflection outside of the solar corona. As near as I can tell, that's something that he thinks should happen, but unless you have any actual data to the contrary, then I don't know. But in order to measure that, that would be even smaller than the hair width at 10 meters, going further away from the solar corona. It's probably tough enough to measure that amount of angle change when you're right up next to the maximum gravity power. And it would be ridiculous to see if you're like 2 or 3 solar distances away, and with gravity falling off is 1 over r squared. I mean, the differences would be, like a hair at like a mile or something like that, some incredibly small distance. So he did claim that, this has been replicated over and over again. I also have my doubts on that, as I've never actually seen anybody else actually trying. These experiments are very expensive and difficult to do. You would think someone would have done it with modern equipment, but I am unaware of any such replications. Although we can now see by looking at these, like they call them Einstein rings. You've seen these pictures, they have the picture of what looks like a galaxy bent around some background object. So definitely the light is getting bent in those instances. So while I might not believe Eddington's experiment, I would certainly believe just a straight picture taken by the Hubble telescope that shows what looks like a galaxy being bent behind some large, massive gravitational object. So for me, it's like, okay, I would agree that light can be bent by gravity. Now, I don't know there's been any analysis done to show that corresponds with what general relativity would predict. I myself am skeptical, because I don't have any problem with light being bent by gravity. It would just be, but as a refractive effect, because gravity probably affects the refractive index of space, especially since I think it's a material substance, and gravity compresses and makes denser any substance, just like if you were at the bottom of the ocean, that is much denser and has a different index of refraction than if you were at the very top of the water. And if you've shown a light through the ocean, you would also see a bending effect. And this would not be due to so-called, space-time, which I don't know what space-time is. That seems like a completely imaginary and made-up concept in my mind. I don't know and I don't think that space-time as a distortion can bend things, right? And I especially don't think it could cause gravity. And from the discussion, you could clearly see even the person who is, fully in favor of general relativity can't really explain at all what gravity is. And basically had a whole discussion. He just gave a shoulder shrug. Said, well, yeah, what's up with that? They try and say things like the space-time distorts such that it causes things to move. That's what he said. But that seems ludicrous. I mean, if I took space-time and treated it like a blob of jello that I could stretch and compress, and I put 2 peas in that jello, no matter how much I expand or compress that space or warp it, those 2 peas are going to stay in the same spot. There's not going to cause no twisting or anything I can do to space to cause 1 pea to spontaneously move towards the other pea, which is what gravity seems to be. The interviewer, he wanted to have the more common sense explanation that we have this big mass somewhere and it has something that's affecting this other little mass over there, like an electrostatic force or something like that, because we understand electrostatic force but we don't understand gravity. And I still think that what the interviewer is getting at a very important thing, which is that gravity, just cannot be conceived as this distortion, twisting or compression of space or space-time, whatever the heck that is. That intuitively we still want to think of gravity as being something that is that can be collected by some mass, and it sends out some kind of force to some other object and causes it to be attracted. And it doesn't mean that very large objects have to be attracted, because my very small bit of mass that I have sitting on my desk, like this watch, very small compared, like this glass is very small compared to the mass of the Earth, is still, drawn to the Earth with the same force that a bowling ball would. In fact, it's accelerated at the same speed. And that is how we like to think of it, not as some kind of warping of space-time. Maybe warping of space-time can explain why light bends in space. I can imagine that. There's a way you can twist your jello so that the light would refract around the corner or something like that. But there's no way that if there's some particles embedded in space that is going to affect any net directional force on any particles, and nothing like we see with gravity. And finally, there was that thing about GPS not working. The basic formulas of relativity have to be used, because you have to, the truth of GPS is that in order for GPS to work, you have to assume that the center of the Earth is a stationary spot. And you measure all the velocities relative to that. We see the rotation of the Earth, so the surface of the Earth has velocity. In order to calculate when you expect a light beam to hit any particular part of the Earth, you have to compensate for that velocity of the Earth, as if it were spinning around a stationary spot. So that is the truth about how GPS and the relativity formulas work. Although that's kind of strange, because we think that the Earth is moving through space around the sun, yet we cannot measure that velocity. We don't have to take the velocity of the Earth around the sun into consideration in order to get GPS to work. Instead, we have to pretend that the Earth is at the center of the universe, stationary, and is rotating around that spot. That is the actual set of assumptions that GPS uses. And then we have to use the velocity minus c over square root, that formula, to predict when the beams coming, the radio beams coming from the satellites, is going to exactly intercept our GPS receivers. So in some ways that contradicts, the basic, what people think are the basic postulates of relativity, which is that, the speed of light is the same in all frames of reference. And, people can't really conceive of how that works. How can the speed of light be the same if I'm running towards the speed of light? Is the recorded speed of light still the same? And the answer is, I would say no. The speed of light would seem faster to you. And me personally, I think what it should be is that the speed of light is the same regardless of the speed of the transmitter, is what Einstein really said. Is that no matter what speed the transmitter is moving, you as a stationary receiver will receive it at the same speed, right? I think that probably makes more sense. Or it makes more sense if the Earth were in fact stuck in the middle of the universe and not moving, that the speed of light that you could emit from any point in that universe would be traveling at the same speed, which is what that actually means. Not that you are receiving it at the same speed, but that physically it travels at the same speed using a particular frame of reference, which would be the center of the Earth. So that's what that's what I think is also the main truth about Einstein's postulates. But only if you think the Earth is the center of the universe, like pinned to some location in space. And like I guess my final comments about gravity is that, you know, I would agree that that gravity really is a force which is accumulated by mass. In my own theories, gravity is just say it's an electrostatic. It's an attribute of the electrostatic force. So you think of the reason why the little particle is attracted to the big ball is because there's an electric force going on here. So the ball is like positively charged. The other particle which is attracted is maybe neutral. And what is happening is that the charge field is causing that dipole to align towards the charge source, and then that difference in force is dragging it towards the other object, which I think may make more sense. So that's my take on the discussion. So I see Pal has raised your flag. So Pal, it's your turn. And Jim. Go ahead, Pal. I think you're muted. Let me see if I can unmute you there, Pal.
Pardon?
There you go. We can hear you.
I just turned the camera on. Can you hear me?
Yeah, we can hear you now. So what do you think, Pal? What about this whole Einstein being famous because of this one experiment? You still there, Pal? Well, maybe Pal is having some problems, but Jim, you also raised your flag. You there, Jim?
Hi, can you hear me?
Oh, yeah, we can hear you now. Go ahead. Well, so what do you think?
Yeah, I think the idea of refracting light by the gravitational potential is consistent with C.C. Sue's local ether model, where the density of the ether is proportional to the strength of the gravitational potential. And in fact, he shows quantitatively that if you assume the speed of light is affected by the density of the ether, according to the strength of the potential, that is slower at a higher potential, that you can retrieve the light deflection and gravitational deflection much more simply than with general relativity. And in fact, also the Shapiro delay, which is measured by microwave signals grazing the sun, is also consistent with that formula. So I also dispute Dowdy's hypothesis about the sun's corona, because I think it's been found that there is also deflection and delay even away from the sun's corona.
So who were you saying confirmed, or at least
Ching-Chang Su, I've talked about him before. He has a thesis called the local ether model that he's developed into a book called Quantum Electromagnetics, and also several papers that appeared in peer-reviewed journals. His thesis is that the local ether of a celestial body only extends out to where it becomes overcomes by a larger celestial body. Like like you were saying, the Earth is in the center of the universe, but it's the center of a halo of ether that is carried with the Earth as it orbits the sun. And then if you go far enough out into interstellar space, you are in the domain of the sun's ether. And then you're farther out, and you go to the galaxy cluster, CMBR. So you don't need to assume that the Earth is the center of the universe to accept the GPS pseudo-range SAGDEC pseudo-range correction that you were talking about.
Yeah, it could be that we are dragging around our own little bubble of ether, which would also explain why is that we don't have to compensate for the speed of the Earth around the sun, and also why Michelson-Morley type experiments fail to detect that velocity as well.
Well, also, Sue's proposal is that the Earth rotates within this halo. It doesn't drag it rotationally around with it. It just carries it inertially, like the ECI, the Earth-centered inertial frame, which also explains why the Michelson-Morley experiments to date have come up empty, because they've been looking for a much higher velocity. The actual velocity, as shown by the GPS pseudo-range correction, is just the Earth's rotation rate. And the Michelson-Morley experiment on the surface of the Earth should be should try to detect that velocity, but the experiments so far have not been sensitive enough. So others have proposed that the Michelson-Morley experiment be repeated in low Earth orbit, where the orbital speed of the spacecraft would generate the Michelson-Morley ether wind.
Yeah, I would like to see these experiments performed in space, or at least far away from Earth. Certainly, we have satellites.
So if you go into interstellar space, then you'll get. If you go into interstellar space, you'll get the full 30 kilometers per second of the spacecraft's orbital velocity around the sun, because the mass of the spacecraft is too small to generate its own local ether halo.
Yeah, I would think, though, that that kind of data should already be available, because as we send out space probes like Voyager and such, and those are way outside of what would be the Earth ether, and we send very precise radio waves to these spacecraft in order to determine their range. Although, spacecraft like Voyager do have this mysterious acceleration or blue shift or something that they can't explain, but definitely they have to transmit through what would be our ether bubble, and that would, I would think, definitely have some effect on when we expect to receive the signals from them. But I think that the data might already be there and might be actually buried, or it just might be just brushed off as an anomaly. But if it were to be looked at, that perhaps it's already there, showing that we are sitting in an ether. There's evidence that we're sitting in an ether bubble. But it would be nice to just have a direct experiment to send an interferometer out to like the middle of the orbits between Earth and Venus, or somewhere where we don't think that the gravity is very strong, and far away from any gravitational source, and see whether we could measure the orbital period of the satellite directly, unlike we can do here on the Earth. So, Ian, you've raised your flag.
Yes, thank you, Franklin. Just a couple of further observations. I found most of what has been said now quite interesting, and I'd agree actually with most of the observations. But just maybe two or three further points. First of all, with regard to the verification of supposed verification of GRT, it's interesting that none of it has been concerned with the theory per se. You know, whether one can prove that space-time is interlinked and curved and all that sort of thing. But it's been based on very specific anomalies. I mean, one might say that the curving of light beside an object has nothing specifically to do with the general theory of relativity. It's just a slight anomaly. So what they've done is they've looked at a couple of points, like the deflection of light and the supposed measurement of the secular precession of the perihelion of the orbit of Mercury, and change in frequency in electromagnetic radiation in gravitational fields. So these are the sort of things that you know have really just sparked the imagination. They're not verifications of the theory itself, and I mean, one might even go a little further and say that they're what has caused the hysteria, because that's really what you had in 1919. In November 1919, it took them 6 months to analyze all the results, bring them back. They were comparing the results they got mainly with results taken in some months before that. But I think it took about 6 months before they were able to get all the results and have a joint meeting of the Royal Astronomical Society and the Royal Society, and then announce the results. But there was hysteria, as evidenced by the headlines in the papers the next day. Einstein is the only scientist on record who had a ticker tape reception in New York subsequent to that. And the crowds were coming out. It was like some sports hero. And they were just going wild and fanatically and responding and so on. So that's my first point. The second point is interesting, what you've been talking about just now about the MMX and the desirability of maybe performing an experiment of that nature in low orbit or maybe in outer space. This was suggested by say Dr. Carl Zapfe, and I thought it would be quite an interesting thing to do. And as you've been saying, as Jim said, and as you said, this would perhaps give some results. But actually, in contradistinction to that, I think that this sort of experiment about the possible deflection of electromagnetic radiation near a gravitational mass would probably be better served by a terrestrial experiment. I mean, Henry Cavendish first started doing experiments about the gravitational attraction between masses by Earth experiments, you know, by looking at things like the movement of pendulums near large masses and so on. And I think that this sort of experiment, looking at the supposed deflection of stars near the sun during a total eclipse, we've mentioned all the possible errors. We could argue until the cows come home as to whether refraction is a big effect, as to whether Dowdy's ideas are right or wrong, or even partially right. There are too many variables there to pronounce upon this. I think if you could analyze some very accurate experiments near a large mass with electromagnetic radiation and modern equipment, this might be able to determine how. My own view is that you would actually verify Soldner's formula for the verification. But anyway, that would be something that we could do in the future. And the last point I want to raise at this point was actually related to the first point, but maybe goes a bit further. Just to remind you that Sir Arthur Eddington was a Quaker and a pacifist, and he would not take up arms during the First World War, and he was in danger of being imprisoned, as a lot of conscientious objectors were then. And the authorities in Cambridge made a special representation to the British government that Sir Arthur Eddington was a very pronounced and prominent astronomer, and that if they would excuse him from military duty, he would continue doing research in Cambridge instead of being locked up in Pentonville prison during the course of the war. And there was an eclipse coming up just in 1919, and they would hope that the war would be over by then. And Sir Arthur was extremely interested in the modern ideas of a German scientist who had 10 years before that brought in the ideas of special relativity, and he would lead an expedition to prove that this German scientist's predictions were right, because Sir Arthur believed that they were. And therefore there would be a sort of like a détente between the two opposing parties in the prison. So that's actually what happened. There was an earlier expedition, the details just escape me now, but and was actually caught just as war broke out. I've just forgotten the chap's name, quite a famous person, but he brought some equipment to Russia, central Russia, I think, and he was looking at an observation of the total eclipse of the sun in 1914, during the summer of 1914. And of course, the war broke out, and this German with Krupp's equipment, which couldn't be identified by the Russian military, was found in the center of Russia, and the war had just broken out. So they interned him for the course of the war, and that put the kibosh on any further experiments there. So this thing seems to have been a complete fiasco in a way, because I feel that the experiment by its nature is probably bound to fail. There was cherry picking, to use your own terms. That is very true, Franklin. But also, Sir Arthur Eddington decided that he was going out to prove the theory right, not going to test it. It's bound to fail because of all these unknowns and uncertainties, even with modern equipment. And I'm suggesting maybe a terrestrial experiment could be done. But on the other hand, it's only one very tangential aspect of the theory of relativity. It's not no test of the basic thesis of the general theory of relativity, that you have a warped space and that gravitational interaction isn't due to a force per se. That has never been done. And the whole political nature of it, giving rise to mass hysteria, really, I think should be noted. But apart from that, I was interested in the comments, and I'd be interested to hear other comments. Thank you.
All right. So who else do we got? Let's see. Did anyone else raise their flags? Pal, did you want to chime in now?
Yes, I tried to put the question also in the chat, but somehow it didn't go through either. Can I just ask my question again?
Yeah, go ahead.
My question was, are there any experiments on separation of space and time? Are they separable or not? I mean, do we know for sure one way or the other? And the other question I had was about Newton's gravity. Newton never really defined gravity. And I'm asking if in 300 or 400 years since then, somebody has given a good definition of gravity. I mean, if Newton couldn't define it, he only said, hey, I don't know what gravity is, but this is how you can calculate it. And so he gave the general formula for calculating gravity, and that substantially has not been challenged.
Well, I suppose I could give a stab at your questions.
Okay.
Which is, first of all, the question itself is strange, which is, can you experiment that separates time and space? Now, I consider those two things to be completely different things, right? So that'd be like asking, are there any experiments to prove the separation of apples and oranges? And I would say, well, yeah, because they're obviously two completely different things, right? So you wouldn't necessarily need an experiment to say that they are separate. What would be odd is if I came up with an object called apple orange, right? If I say that the phenomenon as taste is due to the warping of the apple orange, then that would seem to be complete nonsense, right? But that's kind of the way I see them saying that gravity is the result of the warping of space-time. That makes about as much sense as saying that flavor on my tongue is due to a warping of apple orange, right? That's kind of the way that I kind of see that. So, in which case, it's just complete nonsense to say that they're something that they're together. I mean, I would say that time happens while space exists, so they exist together as phenomenon. And once again, my confusion on the whole concept of space-time is, what is the relationship of time with space, and especially its ability to cause gravity. So I mentioned something about the difference between special and general relativity. So I think general relativity is the thing that's trying to explain gravity, and general relativity is a thing that's just trying to explain differences in light speed, I suppose, or measuring light speed, or its effect upon clocks, maybe. But I'm still looking at that. And as to your second question, I think it's well known that Newton, gave a big shoulder shrug as to what causes gravity, and our current replacements is in fact general relativity. So if you ask a mainstream scientist, what is gravity, he'll tell you about general relativity, about it being a distortion of space and time. Although if you believe that, I got a bridge I can sell you, honestly, because no one can really understand how that possibly works. So that has kind of been in the realm of us dissident scientists who have come up with all kinds of theories. My personal pet theory is that gravity is, in fact, an electrostatic force, that the Earth is just simply positively charged, and we are stuck upon it in a massive case of static cling, and that's all there is to it. Others have proposed that the Earth's surface is actually accelerating upwards at 9.8 meters per second. And what we're feeling as gravity is, in fact, just literally an inertial effect. But you have to kind of believe that the Earth is exploding at 9.8 meters per second and that everything is accelerating outwards. But, that is one of the main theories. The other theory is that there's actually something raining down on us all the time. And this is the Lesage type gravity, where there's these particles which are constantly hitting the top of our heads and pushing us down like some kind of rain. And they think that's gravity. That's another popular gravity theory. And the joke theory is that there is no gravity. The Earth just sucks. So I don't know what you think about those, pal, but that's how I kind of answer those.
I'm still not clear on what you said about apple orange example. Don't you believe in the hybridization of agriculture and how many things they have done, like apple orange as a single fruit? You can't say it's apple, you can't say it's orange, but it's got the taste and something of both. And they can do just about hybridization of any two things these days, as long as they're of the same quanta and qualia. I mean, you can't take a stone and a cat and say hybridize them. But they have to have some comparable quanta and qualia in order for them to be hybridized.
Well, I think your analogy of a stone and a cat is probably more accurate, since you might be able to hybridize the properties of an apple and orange. You could create a candy that contains apple
And
and
that's
orange.
the example you gave me.
But you cannot hybridize a stone and a cat, right? There's no two properties that are even remotely similar that you could hybridize. So I treat space-time like stone cat, right? This is two completely different things, have no relationship to each other. To bring them together is just a crime. So I would say that
often space-time are used as a single entity.
Well, I don't know how space-time is used as a single entity. That's always been my criticism. I could never see how space-time is being used as a single entity. And I don't see how a warpage of space and time could cause any kind of force. And it just never, ever, it's one of those things where I just like, that just doesn't make any sense. No sense at all.
But what do you think our world in which we live, in this world, are we space-bound, time-bound, both bound, neither bound?
Well, in this world, what we consider the volumetric geometric area that we move around in is space. And in my preferred pet theories, space is filled with matter like us, but is also, even in the vacuum of space, filled with positron-electron dipole C, which is also matter. So all of space is, which you can measure with a ruler, is filled with particles. So that's what I think space is. Now, what time is that these particles are allowed to change position relative to each other inside this sea of particles. And what we call time is whenever that state changes. So if we are in a state where the state never changes, then that would be particles without time. There would be no, if nothing ever moved, there would never be any time. But since we do have state changes, you know, I can take my calculator and move it from here to there. That changes state. That process of changing state is what we call time. Now, further to that, I would say that time, as with most things in nature, actually has to be quantized, which means it can only come in incremental units. So, like if you see the watch hand and it ticks off, 1 second interval, say that's kind of quantized time. The second hand can't be thought of as being somewhere in between, although you would, if you had a fast enough speed camera, you could see it. But ultimately, I think that time itself is quantized, and that there is a fastest speed that anything can happen. So I think that is related to the speed of light. That is why there is a speed of light, because light is moving as fast as it possibly can within this particle medium. And it's like there's a master computer clock, which says that if you were to look at that actual light wave, you would see it not move smoothly, but it would go deep. It would move some increment according to the smallest bit of time and according to the smallest distance that we have. So I would say distance is quantized, time itself is quantized. And I just say that just to give time a more physical, actual meaning, so that time is not a continuous thing, is what I would add. So what do you think of that, pal?
Well, I think time is also entropic. It's one way. There's no way to recover it. But space is not like that. So there are differences and similarities among everything, but the fact that time is one way and it's entropic, like the thermodynamics second law and stuff like that, those are things that I don't grasp.
Well, one thing I wanted to point out here, and oftentimes we get into discussions of relativity about what it means to slow down time. Now,
Yeah.
me personally, I think you cannot slow down time. Time only travels in one direction. But what we do observe is that if we build physical clocks, we can see that those clocks slow down. And that's what we actually mean by time dilation, not that time itself slows down. Like I say, I'm advocating that there's actually a universal clock that is actually ticking at the same rate all the time. But if we have a physical clock like a pendulum clock, and if you were to stick the pendulum clock in a colder environment, that actually shrinks the pendulum, and it actually will tick slower. Or if you put it in a warmer environment, it takes longer. And that is the kind of time dilation that I think Einstein is talking about, that it's the effect upon physical clocks, which is slowing, and it's not actual time travel. So, for example, if you have the twin experiment where you send one twin out at extremely high speeds out into space, they're saying that time for him is slowed down. I would argue, no, time for that twin has not slowed down. What's slowed down is his chemical reactions and the physical clocks which he is carrying on board. That is what is slowing down. Because as you travel faster through this medium, you're zipping by many, many, many more particles, right? The volume of particles you are passing by greatly increases, and that causes, like anything that's traveling from point A to point B, to have to travel a lot further. So this is the actual nature of what causes clocks to slow down due to velocity. It's like the difference between moving a spoon through water, which is very thin, or moving a spoon through molasses, which suddenly becomes very thick because there's just simply a lot more particles that you have to push through. So I wanted to make that as kind of an argument about what is time dilation in relativity. But fundamentally, I think time itself cannot be altered. Time itself cannot be slowed down, cannot be sped up. You cannot go back in time. But clocks themselves and biological processes can be slowed down. Now, the other example I bring up is if you take a steak and you stick it on the counter, and you stick another steak and you stick it in the freezer, is the freezer a time machine? Because the freezer will keep the steak fresh indefinitely, as it had been frozen in time. And the steak in the counter will start rotting within hours, right? So would you call the refrigerator a time machine? And I would argue, no. Time has not changed for the steak in the freezer or on the counter. What has changed is the rate of the chemical reactions that are happening in the freezer, which are greatly slowed down in the freezer. But time itself has not changed, and the refrigerator is not a time machine, although you could still kind of think of it as a time machine, because a month later you could take the steak out and it would look the same as the steak that you had just put out in the counter, as if you had transported it by time into the future, right? So, but that's another thing about time that I wanted to kind of point out there, that you can't really change time. I would agree with Powell there. You can't change time. You can't travel in the past. You can't travel in the future. It just happens, and I think it happens at a quantized rate.
So, Franklin, is our perception of time here on Earth the correct rate of time in the universe?
It could be, in the sense that we were talking about the Earth dragging around its own ether bubble, which means that we're effectively at zero velocity, other than the rotational speed of the Earth. So I would take that would mean that if we're at zero velocity, that means that the clock mechanisms would be running at their fastest possible rate. So if you could pick any rate of time in the universe, I think it would be proper that if there was a limit on the rate that time to progress, that you would pick the fastest frame versus the slowest frame, right? So in that way, I would say yes, the Earth is the proper frame of reference to measure time in the universe. How about that? Okay.
So you're saying then that there's no place in the universe that the rate is faster than it is here.
Yeah, probably not.
Actually, GPS satellites tick faster the farther away they are from the surface of the Earth. The gravitational effect. So if you go out somewhere where the gravitational potential is very low, the clocks would tick even faster.
Well, I suppose that would be true. You would have to compensate for the fact that not only do you need to be stationary, but you need to be outside a gravitational field.
Gravitational potential, not field. Field is the gradient. The potential, you can have it's the potential that is a scalar due to density that affects the speed of light and the clock tick rate. Also,
but once again, my point was that the speed of time doesn't actually change anyway.
I'm not saying the time changes. I'm saying
able to measure the quanta of time that would actually be resistant to time dilation effects. So
okay, I agree that time is absolute.
Clock, you would measure the time it takes for an electron to transition from its lower to the very next level, and you would have to be able to measure that time period. Because I theorize that does constitute the smallest bit of time. And if you built a clock out of that, then you could send it. It would not matter what the gravitational potential is. It would not matter how fast the velocity is. It would be shown to clock tick at exactly the same rate, whether it was here or in Alpha Centauri. But that's only a theoretical consideration. But
Actually,
a totally positive physical attestation of time as being a physical thing that is absolute everywhere, immune to relativistic effects.
Actually, Suze derives a wave equation that shows that the transition energy and therefore the frequency of atoms in an atomic clock is affected by the gravitational potential. In which case, which explains why the atomic clocks on GPS tick faster than they do on the Earth.
Well, everyone's free to speculate on everything.
Sorry?
So I would just like to say that may be true, that may be false. Anything that has distance comes up with is quite suspect.
But I agree that time is absolute everywhere.
Yeah, time is absolute everywhere. That's what I'm going for.
And another point against special relativity is that GPS clocks tick slower because of their velocity. But it's only their velocity with respect to the ECI, whereas special relativity would claim that it's a relative velocity between the observer and the clock, and the GPS satellite.
Well, another interesting factoid is that, let's see, someone is echoing here, so if you're not speaking, please mute. Is that, yeah, who is echoing here?
Actually, Franklin, it's just you.
Is it just me?
That's what it sounds like.
And you've gone even fainter than you were as well.
Well, now I'm getting a really... Because I'm using my phone, I can't normally monitor to see who is not muted. So we have... Okay, I think that was... Okay. So... Now, there are two effects that affect the clocks, and that's velocity, and then there's the gravity. And so you would think that a clock sitting at the equator would tick differently than a clock sitting at the North Pole, because the one going around the equator is going faster. Now, the interesting factoid is that the clocks actually tick at the same rate whether they're at the equator or at the pole. And what they say is that the reason why that is because the Earth gets elongated along the pole. So there's actually, more gravity there than there is at the pole. And these effects actually just exactly cancel each other, such that the clock ticks the same whether it's here or there. Now, I personally find that to just be a humongous coincidence, and I'm not terribly convinced that that's the reason why clocks tick the same everywhere on the Earth, right? It doesn't seem to matter. Or it could be that the Earth is actually genuinely stationary, and that's why the clocks tick the same everywhere.
That effect is only if all the clocks are at sea level. If you have some on top of the mountains, they tick differently.
Yeah, they tick differently. But assuming sea level, they tick the same everywhere on Earth. It's completely ignoring the velocity of the Earth. That's the interesting factoid. Now, there are a lot of arguments from the geocentrists who genuinely believe that the Earth is, in fact, the center of the universe, and they'll point out stuff like that. So that really drives the geocentric. I mean, that drives everyone else crazy. So listen, Michael, did you get your chance? I see you would raise your flag.
Well, the concept of different time rates would be treated in my ether model as there's a universal vibratory ether, which was derived from an original universal oscillation. And then if you have this underlying ether that's universal and it vibrates, then you'd have a vibratory rate. Now, if you have an energized region of space, such as a magnetic field of the Earth or any magnetic field of any body, the vibratory rate would be faster, reflecting the increased ambient energy levels. If you could go far enough out in space to where there's just the ether and no bodies or whatever, the rate would be very slow. So this, the rate of the ether, vibratory rate of the ether itself would be, of an unmagnetized ether, would be the same everywhere. So if you had a more etheric region, even close to the Earth, if it happens to be more etheric, it would have the same slow time rate as outer space, which would be very, very slow, as I say. And this is a correlation between the energy level and the vibratory rate. And the vibratory rate would filter through to the quantum realm as well, because the ether and the quantum forces are connected through transition of etheroidal units to subquantum units and so on. It's all connected up.
Well, I suppose there's a possibility, and you're introducing the possibility that there could be regions of space where things just fundamentally happen faster than some other spot, right? As opposed to the theory that time itself is quantized and ticks the same everywhere. That some place saying that some regions of space could have faster ticks. I suppose that's a possibility. I mean, the rate at which, something has to limit the rate at which something ticks, and I guess that would be a property of space, I suppose. So, but that could be a possibility. Maybe there is this fundamental clock, but that clock could be ticking at different rates in different places under different conditions. I suppose that's what we already observed with atomic clocks, where atomic clocks down on the bottom of the mountain click at a different rate than atomic clock put at the top of the mountain, right?
Well, I think I might qualify the variation in the timekeeping of clocks by saying that it's really atomic clocks which are affected by this Lorentzian type factor. I mean, other clocks will vary in other ways. If you brought a pendulum up to outer space, obviously that would either cease to operate or would give very, very odd readings. And similarly, for a mechanical clock, it would depend on the regulator and the temperature effect. But it seems to be that it seems a coincidence that atomic clocks seem to vary in respect of the relative speed between the clock and the ECI frame, let's say taking the Earth as the Earth-centered inertial frame, and also the gravitational potential between the quasi-stationary Earth and the atomic clock. But I think if you think about it in more detail, maybe it's not so strange, because Lorentz was working on the theory of the electron and vibrations and relative motions and so on. And it was only really extended and used by Einstein then to be, you know, the formulae which apply to all dynamics. So maybe the coincidence of the Lorentz type correction to atomic clocks is not perhaps so strange. The other thing, of course, in the recording is that what they did is they concentrated on Professor, whatever his name was, Coles. He concentrated on this gravitational potential effect. But of course, that's very, very much smaller than the major effect which has to be taken into account, which was mentioned earlier, which is the Sagnac correction for the spin of the Earth. I mean, that's orders of magnitude greater, but obviously that's not really considered by relativists. It's sort of kept it quiet.
Well, that did remind me another thing that I had to say about atomic clocks. It's always been a bugaboo for me. You know, you mentioned the difference between, say, a pendulum clock and an atomic clock, but actually it turns out the way that an atomic clock works is that behind the scenes is there's actually there's just a simple quartz crystal, the same kind of crystal that you would find in a common wristwatch like this. Now, the difference between my wristwatch and an atomic clock is that they're using the cesium atoms to create a feedback loop, such that if what would normally happen in my crystal watch here is that it would try and speed up or it would slow down. But by using this feedback mechanism with the cesium atoms, it's kept at a very, very precise resonance, or what you know, the natural frequency at which the crystal oscillates. So the oscillation is kept extraordinarily stable. You know, the atomic clock is often kind of mentioned as if it were actually using the cycle of the, you know, it's like something like 9 million hertz or something like that, which is the transition of the electrons from in the cesium atom, as if we were actually using that to build the clock. Now, I would assert that if we were actually using that, then you would actually be detecting the actual tick rate of the universe, and you would find that would generally be immutable. But we're not actually doing that. Behind the scenes in an atomic clock is still quartz crystal, and what we are measuring is the oscillations of that physical quartz crystal, which is physically waiting in space, generating oscillation. So in many ways, that quartz crystal is very similar to what you might find as a pendulum in a pendulum clock, or if you're in an ordinary wristwatch, you have the little oscillating spring. It's still a physical thing. And because it's a physical, literally a fork traveling through space, I mean, there's some finite amount of space that it's traveling through to do that, then it is fully subject to environmental conditions that I would claim affect the rate of time. So if you put it in an environment which has a denser ether environment, that is going to slow that crystal down. Now, the universal clock that they're using, the Sesamian atoms, will keep that oscillation absolutely stable, but it's not going to stop the actual crystal from slowing down because of the changes in the ether environment, right? What I would like to see is an actual clock that actually measures the transition time for an electron around an atom, or it would have to measure the transition time. You would have to be able to take a picture of, say, an electron that's moving, and you would have to be able to measure, well, you first would have to observe that it's moving in quantum leaps. And there are experiments, like there's these neutron dropping experiments. That's like a neutron, they'll drop it, it'll hit, and it won't bounce and hit the target at just anywhere. It will only bounce at quantized locations, which shows that the neutron itself, when it's dropping, is actually not dropping smoothly. It's actually dropping in incremental motion, right? So it can't bounce and then hit any arbitrary spot on their experimental target. So that's like a bowling ball, which can only fall in 1 foot increments, right? So you can see the bowling ball, and you'll see it 1 foot and another foot, but you'd never see it anywhere between. It would never be like 1.5 feet, dropping from 1.5 feet. And you would never see that energy. So all those things kind of imply that things can only move incremental distances over incremental times, and that you could create a clock which actually takes advantage of that. Then I think you would find the absolute tick of the universe. And, like Michael said, maybe that tick happens faster or slower in maybe different places. But fundamentally, everything is driven by that tick, I would say, at least in my crazy dissident science universe, which we like to discuss here in CNPS. That's the way I like to see it. But, my main point being that the atomic clock, not so much different than your wristwatch or from a pendulum clock. So we have anyone else would like to make a comment on relativity or anything we've discussed here? So someone just.
But by the way, just while somebody is thinking there, just a quick aside. They mentioned on the clip that the equipment was manufactured by the company Howard Grubb and Company in Dublin. Now, the coelostat is actually still existing, and it's on display in Dunsink Observatory in Dublin. So just a matter of interest. I actually have a poor picture of it here if you wanted to see it. It's I don't know. Well, it's let me see. Rather than waste time, it's a poor picture, so I don't suppose you can see that, can you?
There's some UFO-looking object there.
Yeah. Well, anyway, that's the coelostat, which Eddington used, and it's on display here. Howard Grubb and Company was a prominent optical manufacturing company at the end of the 19th century, the beginning of the 20th. They manufactured a lot of equipment like periscopes for naval vessels and so on. So, just anyway, as an aside.
Yeah, my main problem with that experiment remains to be there's just no way they could have measured it to that degree of precision. I could believe.
I think there seems to be a general agreement on that. I'd like to know if any of us today disagree with that. I mean, I certainly agree with what you've said there. Does anybody disagree?
Yeah, does anybody think this is a legit experiment? Right. What I don't get is, like, what was a gigantic? Because I was looking at the article in the New York Times about this. They said they had the lights askew in the heavens. So I looked up the New York Times, and if you search for that on the internet, you can find the actual original November 9th article, and you can download it in the PDF. And it's like, well, how did that happen, right? It's like even if it was totally true, it's like, why would they pick up on it? It's like Einstein made a deal with the devil or like some blue genie. He said, "Make me famous," and suddenly someone publishes this on this, because I'm pretty sure that, say, if my theories on what space was, the University of Washington conducted some experiments which proved beyond the doubt that these positron and electron dipoles, I'm sure it would be published in some obscure article and no one would care, right? As opposed to it being published on the front page of the Seattle Times saying, scientists have discovered what space is made out of, which is, effectively what this article was like, right? So,
you see, I tend to think that this was I almost said in the ether, but it might be more appropriate to say in the water at the time. I mean, remember, for years this experiment had been mooted, and they were a good 6 months analyzing the results. So I think the journalists in the know would have been informed by all the scientists. Oh, do you know what? We're working very, very hard. We've spent a lot of money on this expedition, and it's going to take us months to analyze the results. But be careful, or just be on the lookout. We're going to verify this new theory. It's going to be an amazing thing. And the thing got blown up, and they were all expecting this. And they said, "Oh, we think we're going to have the results next week. Just wait for it. Oh yes, it'll be November." And then the results come out, and all the journalists are waiting for it, and they're preparing something that they decided in the first place actually that they were going to prepare. Sounds a bit cynical, but I think we've seen it nowadays, this type of thing.
Yeah, I guess the equivalent would be the announcement of the Higgs boson, right? That was pretty up,
yeah.
Right?
And even the term splitting the atom, I mean, that was introduced by the journalists, sort of in the 1930s, 1920s, 1930s. And who's going to split the atom first? And who has split the atom? What is splitting the atom? I mean, I've mentioned before the Cockcroft-Walton experiment, which was the first artificially induced transmutation. Was that splitting the atom? Was Rutherford's experiment, doing it by natural means, by radioactivity, was that splitting the atom? Was fission splitting the atom? It was a term which the journalists said, "Oh, he split the atom, splitting the atom." And the scientists took that on and they started using it. And as you say, the Higgs boson is probably the more recent example of that. And actually, the extract, the audio file which you permitted me to play, I think was useful in a number of respects, dare I say, because it's a populist thing. It's appearing on a populist program just a weekday morning, the ordinary man and his wife listening to it. The interviewer is actually an engineer, but he hasn't practiced for 40 years or something. But they're getting something which is nice and newsworthy, but it's rather simplistic. And I was toying with the idea of maybe responding to them. They get these responses in by email or something. I didn't bother in the end, and then I just thought that maybe we could have an analysis of it. But I think our analysis today hasn't really surprised me. And
you should send the entire recording to him, right? Okay.
It's the entire recording. In fact, I had to clip it because it started with Tony Blair and it finished with some other rubbish. So I had to clip it, so it was only about this. It's just under 14 minutes, I think. But there were no responses.
14-minute clip and talk about it for nearly 2 hours. So.
Sorry, say that again?
We can take their 14-minute clip and talk about it for nearly 2 hours.
I know, yes. Well, that's us. We're long-winded.
Yeah, that's like the most amazing thing that people, when I tell them about the science conference, you talk about something for 2 hours, right? How do you manage to keep that going? But speaking of that, it seems that we have reached towards the end of our time today. And I apologize, we had a number of technical difficulties today with Fuse, which prevented me from logging in my normal laptop. But today we had Ian Cohen. He brought us this interesting recording celebrating the Eddington experiment nearly 100 years ago, which launched Einstein into fame. I mean, prior to this, he was just a dissident scientist like we were. And I guess in some ways I'm jealous, and I hope that it happens to one of us one day where we'll be as famous as Einstein by such a crucial experiment. So that's my goal. I really have to stop talking to you guys and talk to like some experimentalist at the University of Washington or some other major research.
So let's band together.
And have them find my space, right?
So let's band together and get a microsumorally low Earth orbit done. With the Rocket Lab, you could do it for less than $1 million now.
Okay, you got the $1 million. We'll do it.
Start a Kickstarter or a GoFundMe.
No, like I said, I think if we analyze it,
private company
probably already find it. I'm sure someone has probably sent something like an interferometer up space at some point.
Since it's a private company, you don't have to prove to a committee that it's going to have a result, because they'll all tell you no.
All right, you raised $1 million. We'll be there.
Dr. Jaffe had some questions which he posed to NASA about MMX, and they sort of courteously wrote to him in a fairly cursory way. But when he proposed this, they just ceased to reply to his letters. He wrote again. They just ignored him. NASA.
Yeah, with rocket.
You have to cover it up as being a general relativity experiment confirming general relativity. So, with our electronic sensors nowadays, it's probably very easy to send up a solid state interferometer, and then you could just say, as like a high school experiment, say that, this will prove that the speed of light is constant everywhere. Of course, when the results come back, that it's not, and that it confirms that there's a bubble of Earth, there's a bubble of ether around the Earth, then you'll screw them, right? Okay.
And I've proposed, indeed, that we do that. But I've also proposed earlier that we do a terrestrial experiment with regard to the deflection of a ray of light or an electromagnetic ray by a large gravitational mass. I think that could be done with modern equipment. So in other words, a repeat of this experiment, but terrestrially, to see whether it would be far more easier to believe that you can get a high accuracy repeatable experiment on a terrestrial basis versus trying to measure the starlight bending around the sun, which is super difficult with the wind shaking and humidity and all those other things. Now, if you put this in a very nice stationary laboratory like they built at MIT to do all their micro stuff, I could believe that. I mean, after all, we can measure the strength of gravity around small objects like Cavendish did, right? Certainly, if we can do that, we should be able to directly observe deflection of, say, a laser beam around a large gravitational object, which could be as large as a building, right? So,
but the only way to really disprove Einstein's relativity is to present them with the experiment that started it all, the MMX, and show that it does have a positive result if you do it
right. Maybe, but probably not.
Well, actually, we already have a positive result. Probably from the original 1887 experiment, there's a very small variation, and from later experiments like Miller's and so on. But they explain those away. They dismiss them, as you know.
Actually, my unusual stick on Einstein is that I actually think he's correct. That if you actually read what he actually wrote and apply that is absolutely correct. What happens is that people read things like, the speed of light is constant relative to the stationary frame, and then they convert it into the speed of light is constant in all frames, which is completely different. Then,
but if the velocity is only that matters is only the velocity of the rotation of the Earth at 350 meters per second, all those experiments weren't sensitive to find that. Even the most modern precision experiments today can't unambiguously measure that. It's too small for a second order experiment. The first order experiments,
speed and Sagnac experiments.
Those are first order. They're much.
But, you know, they did do more sophisticated MMX type experiments. I forget the guy's name, but you know, he did it up in a mountain, and you know, he did find yearly.
That was Miller. But if you look at his results, he's averaging tenths of a fringe shift, which doesn't really work.
Yeah, well,
you need something that's you know, unambiguous, that you can't dispute. That's why you need MMX in low Earth orbit, where the speed is of the spacecraft is 50 times.
The later maser and laser experiments seem to indicate that you know, there's a zero effect. But we know that was it 1979? It's the
Brilliant Hall.
Brilliant Hall, exactly. They just dismissed the variation as random, and then if it's analyzed in more detail, it's actually the spin of the Earth which is showing up. But I've looked at some of these, I think with you, Jim, but some of the later ones are claiming to have got rid of all these effects and, you know, showing practically zero effect. But I'm just suspicious as to whether they are also dismissing some variations because they don't fit in with their ideas. I don't know. I haven't actually analyzed all those latest experiments. They claim to be going back to something like 10 to the minus 12 in accuracy.
Well, they're averaging over days and weeks and months, whereas this phenomenon would be constant over a day. Overall, it's the same velocity. They're looking for a velocity that changes with the orientation of the Earth, essentially against the CMBR. And by averaging the two omega signal out, then they can claim that it's not there. 2 omega would be due to the Earth's rotation.
That's the rotation, yeah. Well, probably they're effectively doing the same thing as they did with Brilliant Hole then.
Exactly.
Okay.
All right. Well, we've come to the end of our hour here today, so I thank Ian for bringing us the recording about general relativity and getting our discussion started. So, you know, we brought up a number of reasons why we might be skeptical about that, and discussed, you know, what might really be going on with time dilation and light bending and the other experiments that are involved around that. And if anyone got $1 million, we're looking to do an experiment to send an interferometer into space. Okay, so anyone out there want to give us $1 million or something like that, we'll take your money. All right, but I think that will do it today for today's episode of the Science Chat. And thank you for participating, and we'll see you here same time, same place next week. All right, bye everyone.
Thank you.